thermodynamic processes. Here we have different types of thermodynamic processes. The first one is quasi-static process. Second one is isothermal process. Third one is adiabatic process. Fourth one is isobaric process. Fifth one is isochoric process. Sixth one is cyclic process. So we will learn all these 6 processes in detail now. The first one, quasi-static. Static means stationary. Quasi means nearly stationary. So it is an ideal process in which it is an ideal process in which at every state the system is in both thermal and mechanical equilibrium with the surroundings. In thermal and mechanical equilibrium with the surroundings. So for this process to take place, the process should be very slow. So this process must be very slow process. For example, if you take a balloon here, if you press this balloon consists of some gas here. If you press the balloon suddenly, what happens? The molecules will get large kinetic energy. Due to this, the temperature of this gas will increase, the heat energy in this will increase. So this is a sudden process. But if you compress this slowly, very slowly, then the temperature of the gas may change or may not change. It will take very slow process, and the change in pressure in this case is nearly zero. Change in volume also nearly zero from one step to another step. Change in temperature is also very zero. So if it is in this condition, then it is said to be in thermal as well as mechanical equilibrium. So then it is known as a quasi-static process. Now the different processes are isothermal, adiabatic, isobaric, isochoric and cyclic process. So first let me complete this cyclic process. What is the cyclic process? The process in which the thermodynamic variables return back to its original position or original values. Now, if you take a PV diagram here, indicator diagram, so here it is shown like this. What is the meaning of this one? Here the process, let us start from here. It undergo this process and it went to this different stages there. Here the initial volume is V1, here volume is V2, here volume is V3, here once again V4. So this is the initial state as well as the final state. So this is called a thermodynamic process. So change in volume here is 0 because it is reaching the same volume here. Change in temperature is 0 because it is reaching the same temperature. So change in pressure is 0. So in a cyclic process, as the change in temperature is 0, so we can write here change in volume is 0, that is only for the initial and final state. But here volume increased, here volume decreased. This is the change in volume. So it may not be 0, but change in temperature is always 0. When the change in temperature is 0, du is equal to NCV delta T. So NCV into this delta T is 0. So change in internal energy is 0 for a cyclic process. So for any cyclic process, change in internal energy is always 0. Now, next one, this is isothermal process, adiabatic process, isobaric and isochoric. So I am going to explain about this one in detail now. Here, first let me explain about isothermal process. First point, a process in which temperature of a gas is kept constant with changing or with changes in pressure volume is known as isothermal process. So in this process, temperature of the gas never changes, but the pressure, volume and other quantities like heat and internal energy may change, but internal energy will not change. As temperature is constant, just now I told you, internal energy will be 0. Now from this we can write T is equal to constant or change in temperature is 0. So this is the first point about isothermal process. Now second point in this case is, if we want to observe this isothermal process, first of all I need to take a container in which the gas should be taken. So I am taking a gas here. As the temperature is constant, I need to consider these walls should be diathermic walls. So for this process to take place, walls must be diathermic walls, that is conducting walls. Why? Because if you keep this gas in a container with the diathermic walls, and if you heat this one, whatever the heat that is supplied to this one, temperature generally increases. If these are conducting walls, then it may lose the same quantity of heat to the surroundings. So due to this, we can keep the temperature constant. So for this temperature to be constant, the increase in temperature by heating should be equal to the quantity of temperature, that is a quantity of heat that is exchanged between the surroundings. So that the increase in temperature due to heating must be equal to the decrease in temperature due to the exchange of this heat between system and surroundings. Then when these two are equal and opposite, net change in T will be 0. So change in temperature system will be 0. Now the third one is here, as the temperature is kept constant here. So here T is equal to K. We know that what is the nature of the how the pressure and volume changes here we will see. According to this formula, ideal gas equation, PV is equal to nRT. When T is constant, already number of moles universal gas strength is already constant. So we can write PV is equal to, all together we can denote with the letter K. So this is a constant value. So P is equal to K by V, or P inversely proportional to volume. So whenever temperature is constant, pressure of this gas is inversely proportional to temperature for volume. So whenever two physical quantities are inversely proportional to each other, the corresponding graph is always a rectangular hyperbola. So I am going to write this as, this is V, this is P, this is PV diagram or indicator diagram. So this is the nature of the graph here. So this is a rectangular hyperbola. So PV graph is a rectangular hyperbola here. Now fourth one, in chemistry you might have studied this. When the temperature of a gas is kept constant, pressure inversely proportional to volume of the gas, or pressure of a given mass of a gas is inversely proportional to volume, then we can say that as Boyle's law. So isothermal process obeys Boyle's law. So it obeys Boyle's law. Next, fifth one, this is the temperature is not changing too much. So as we discussed in the quasi-static process, this process must be a very slow process. So isothermal process is a very slow process. It is a very slow process. So what is the example for this process? Now we know that state of matter changes from one state to another state at constant temperature. For example, conversion of ice into water takes place at 0 degrees Celsius only. So when ice is converting into water, it takes place at constant temperature. So this is the best example for isothermal process. So here I am going to write this one. Example for isothermal process is change of state, conversion of ice into water, as well as conversion of water into gas or vapor. This is an isothermal process. Now the seventh one is, if you take this isothermal curve here, in isothermal curve, what is the slope of the isothermal curve? The slope of the isothermal curve is given by, here I am going to write, as it obeys Boyle's law, so we know that PV is equal to K. Now how to find the slope? Slope is the tangent angle made by the graph. So this is the x-axis. So this is the slope of this graph. Here, how to find the slope of this one? We know that tan theta is equal opposite side by adjacent side. This is V, this is V, this is P, this is delta P, this is delta V. So now we can write delta P by delta V. Change in pressure by change in volume is equal to tan theta, that is the slope of this curve. So here, how to find the slope of this curve from this curve? We have given that the nature of this one is given by that equation, P product of pressure and volume is constant. So once again we will use that UV formula, pressure into change in volume plus volume into change in pressure is equal to, derivative of a constant is always equal to 0. So we can write P into delta V is equal to minus V into delta P. As we need the ratio between change in pressure to change in volume, so this is change in pressure by change in volume, which is equal to minus P by V. So the slope of isothermal curve, this isothermal curve is also called isotherm. A name given for this PV graph for isothermal process is called isotherm. The slope of isotherm is given by is delta P by delta V, which is equal to negative of P by V. So why it is negative? Here angle made in the clockwise direction is always negative, angle and anti-clockwise is positive. That's why slope is negative here. Now, eighth point in this one is, we know that specific heat is the quantity of heat required to increase unit mass of, 1 mole of gas by 1 degree Celsius. Now, here as delta T is 0, what is the specific heat of a substance during this isothermal process, which is given by Q by N into 0. So Q by 0, something by 0 is infinite. So the eighth point is specific heat in isothermal process for any substance is infinity. Adiabatic process. Here, a process in which exchange of heat does not take place between system and the surroundings, in which exchange of heat does not take place, but that means quantity of heat of the system remains constant or we can write change in heat energy system is 0. Here pressure may change, volume may change, temperature may change, some other thermodynamic variables may change, but heat remains constant, so change in heat energy will be 0. So for this system, for this process to happen, we need a container with adiabatic walls. So walls must be adiabatic walls, that is adiabatic means insulating walls, so that no heat exchange takes place between system and surroundings. If it is the container, if you take a gas in this one, now heat will not exchange between system and surroundings. That means no heat enters into the system or no heat released by the system. So this is as it is a insulating wall, heat exchange will not take place. That's why total heat change will become 0. Third case, here as the heat is constant, here Q is constant here. So it does not obey this PV is equal to K. Instead it obeys another law which is known as PV power gamma is equal to K. So it obeys this law. According to this law, if you draw the graph for this one, here isotherm is a rectangular hyperbola, whereas for this one PV graph, the slope of this graph is more than that. So slope will be more. Here for this one, let me say this is the isothermal curve. Here slope is more. That means angle made by this one with the x-axis will be more. So for this process. Now this is a adiabatic law, and so that's why I'm going to write here fourth one. It obeys adiabatic law. So here the third point is pressure relationship proportional to volume, and it is a rectangular hyperbola PV curve. So here it is not rectangular hyperbola, but having more steeper than the previous one. And the fifth one, as the exchange of heat is not taking place, so it is a quick process. This process takes place within no time. For example, bursting of cycle tire is an example for this one. So adiabatic process, bursting of cycle tire is an example for adiabatic process. Now, how to find the slope of this adiabatic curve? So we know that PV power gamma is equal to K. So let me take this PV power gamma is equal to K. P into derivative of this one is equal to gamma V power gamma minus 1 into delta V plus V power gamma into delta P is equal to 0. So this you can write gamma P V power gamma by V delta V is equal minus V power gamma delta P. You can cancel V power gamma here. So dP by dV is equal, this minus will come here, minus gamma P by V. What is this gamma? Gamma is the ratio between specific heat of the gas at constant pressure to the specific heat of the gas at constant volume. So this is as Cp greater than Cv, Cp minus Cv is equal to, that means Cp greater than Cv, gamma is equal to Cp by Cv. This is always greater than 1. So now as it is more than 1, what is the slope of this curve? The slope of the curve, slope of adiabatic curve is given by change in pressure by change in volume, which is equal to minus gamma times the P by V. So when compared to these two processes with the same ranges of pressure and volume, the slope of this curve is gamma times more than this one. And the eighth one, the specific heat of this gas is given by Q by N into delta T. This is the quantity of heat supplied in this process. As dQ is 0, the specific heat will become 0 by something which is equal to 0. So this is the condition here. So these are the differences between isothermal process as well as adiabatic process also. So sometimes they may ask you to write any 5 differences between isothermal and adiabatic process. Out of these 8, you can write any 5. And one more point is there, 9th point, that I am going to write here. Work done in isothermal process is given by W is equal nRT log V2 by V1. This is the work done in isothermal process, and the work done in adiabatic process is given by W is equal to nR T1 minus T2 by gamma minus 1. So this is the 9th point. Now I am going to derive this work done in these 2 processes, but you can add that one as one of the point here. If they ask any 5 points, you can write any 5 points from these 9. What is the work done in isothermal process? How to find this work done in isothermal process? To find out the work done, consider 1 mole of or n moles of an ideal gas. Why I am taking only ideal gas? A gas which obeys both Boyle's and Charles law at all temperatures and pressures is known as ideal gas. In general, ideal gas is not available in this universe. So this is only an imaginary gas. Only ideal gas obeys this ideal gas equation, which is equal to PV is equal to nRT. That's why to derive all these derivations, I am going to take ideal gas only. So what is the work done actually? Work done is equal to integral of P delta V with limits V1 to V2. Now to find out the work done, we know that in a isothermal process, it obeys Boyle's law, which is equal to PV is equal to nRT. So in place of P, you can write nRT by V. So now you can write this as integral of V1 to V2. In place of P, you can write nRT by V into delta V. So when you are integrating or differentiating, bring the constants outside. This will become nRT integral of delta V by V with limits V1 and V2. I am telling students, you are going to learn now this integration only in the second PUC, but here I am going to give d by dx of log x is equal to 1 by x. This is one formula. Similarly, reverse of this one, that is integral of 1 by x dx is equal to log x to the base e or ln x. So here you can see this is in the form of 1 by v delta v. Here the formula is integral 1 by x delta x or dx is equal to log x to the base e or ln x. Here this is in the form of nRT. This is nRT integral 1 by v delta v or dv with limits v1 to v2. You can write this as nRT log, because by applying the fundamental formula of integration, you can write integral 1 by x dx is ln x. So this is ln v with limits v1 to v2. After getting this value, we can write nRT ln upper value we have to substitute first v2 minus, then you have to substitute lower value ln v1. So this is the expression. So the total work done in isothermal process is given by nRT ln v2 by v1, because log a minus log b is given by log of a by b. So I am using the same formula here, log v2 minus log v1. This is natural log. Log v2 minus log v1 by log of v2 by v1. So this is the work done in isothermal process. Now sometimes instead of this one, in some books you can see this formula as nRT log v2 by v1 to the base e, or in logarithm books all these values are given to the base 10. So we can write this as nRT log V2 by V1 to the base 10. When you are multiplying this one, you should write 2.0236. This is the work done. But we know that in isotope process PV is constant, P1 V1 is equal to P2 V2. So V2 by V1 is equal P1 by P2 here. Now in place of V2 by V1 you can write P2 by P1 also. Here you can see this is nRT ln V2 by V1. So work done in isotope process in terms of the pressures can be given as nRT ln P1 by P2. So this is the 9th point in isotope process. Now the 9th point in adiabatic process, that is work done in adiabatic process. So in this process also I am going to consider n moles of an ideal gas in a container. Now here I am going to find out the work done here. This work done is given by integral P of delta V with limits V1 and V2. This is called lower limit, this is called upper limit. But we know that ideal gas obeys ideal gas equation as it is adiabatic process, it obeys PV power gamma is equal to K. So in place of P you can write K by V power gamma. So here I am replacing this integral of, in place of P I am going to write K by V power gamma delta V or dV with limits V1 and V2. So this can be written as, you bring this K, as K is a constant here, bring the constant outside. The remaining terms are 1 by V power gamma dV with limits V1 and V2. We know the fundamental formula of integration, x power n dx is equal to x power n plus 1 by n plus 1. This is the fundamental formula of integration. For differentiation, d by dx of x power n is equal n into x power n minus 1. This is the fundamental formula of differentiation. This we used in motion and straight line lesson. Now we are using this integration in thermodynamics lesson. Now from this I am going to write K is constant. This you can write integral as it is 1 by V power gamma. If you bring it to the numerator, this you can write V power minus gamma dV with limits V1 and V2. So from this we can write K into integral V power minus gamma dV. So if you take this as x power n, this will become x power n plus 1 by n plus 1. So I am going to write this after integration V power minus gamma plus 1 by minus gamma plus 1 with limits V1 to V2. So from this I can write K is constant. Now you can substitute the upper value first. In place of V you write V2 minus of V1. So this is 1 minus gamma. Let me bring it outside. This is 1 minus gamma for both values. So only you have to substitute this value. So now first it will become V2 power 1 minus gamma minus V1 power 1 minus gamma. Here this is actual minus gamma plus 1, but I am writing 1 minus gamma. So this is the work done in adiabatic process. Now you can simplify this equation further as I am multiplying this K with this one. K into V2 power gamma 1 minus 1 by minus K into V1 power gamma 1 minus gamma by, this is 1 minus gamma. But what is this K? You can see this one, PV power gamma is K. That means P1 V1 power gamma is equal P2 V2 power gamma is equal to K, or even P3 V3 power gamma is equal to K. So in place of K you can write P1 V1 power gamma or P2 V2 power gamma. So here as it is V2, in place of K I am writing P2 V2 power gamma, P2 V2 power gamma. So now the work done in adiabatic process is given by P2 V2 power gamma V2 power 1 minus gamma. This is the first term minus. In place of this, as it is V1, so I am writing P1 V1 power gamma. So this is P1 V1 power gamma V1 power 1 minus gamma by 1 minus gamma. So now you can cancel this one. V2 power gamma, this is V2 power minus gamma, because this is V2 power 1 into V2 power minus gamma. So these two get cancelled. Here also V1 power gamma and V1 power minus gamma get cancelled after simplification. Now the remaining terms are P2 V2. So I am writing here P2 V2 minus, here remaining terms are P1 V1 by 1 minus gamma. So this is the work done in adiabatic process. Now I am going to write this as W is equal P2 V2 minus P1 V1 by 1 minus gamma. But as we discussed earlier, gamma is the ratio between Cp by C, which is always greater than 1. So here you can see 1 minus more than 1, this is 1.2, 1.3, 1.4, 1.5. This value will become negative. So to make this work positive, multiply both numerator and denominator with minus, you will get P1 V1 minus P2 V2 by gamma minus 1. So this is the work done in adiabatic process. But as we know that any gas which is taken ideal in any process, that is isothermal, adiabatic, isobaric, isochoric, cyclic or quasi-static process, it must obey the ideal gas equation. So in this we know PV is equal to nRT. So P1 V1 is equal to nRT1. So work done in adiabatic process can also be written as nRT1 minus nRT2 by gamma minus 1. So work done in adiabatic process is, if you take nR common, T1 minus T2 by gamma minus 1. Adiabatic process, we can write this as P1 V1 power gamma is equal P2 V2 power gamma is equal P3 V3 power gamma is equal Pn Vn power gamma. So this is adiabatic formula, adiabatic equation. In the same expression, sometimes they may ask you to a relation between pressure and temperature or volume and temperature in a adiabatic process. So this is the PV relation of adiabatic process. So what is this PT relation? So now let me take one set of this equation, that is P1 V1 power gamma is equal P2 V2 power gamma. So in this I need PT relation. So I need P, I don't want V. So what I am going to write, P1, in place of this I am not going to write anything, V1. So this is P2, in place of this also I am leaving this. As it is an ideal gas, it obeys PV is equal to nRT. So in place of V you can write nRT by P. So in place of V we can write nRT by P. But as it is V1, N1 R1 T1 by P1. This is N2 R2 T2 by P2. As I am taking n moles of gas, this n get cancels, and R1 and R2 are universal gas constant which are equal. So this relation can be written as P1, this will become T1 power gamma. This is P1 power gamma in the denominator when it goes up. P1 power minus gamma is equal P2 T2 power gamma P2 power minus gamma. So you can write this as T1 power gamma P1 power 1 minus gamma is equal T2 power gamma P2 power 1 minus gamma. This is the relation between PT or pressure temperature relation, PT relation in adiabatic process. Sometimes they may ask you to find the relation between temperature and volume here. So let me take the same expression here. So I am going to write this as P1 V1 power gamma is equal P2 V2 power gamma. So I need a relation between temperature and volume. So I need to replace this P. So here once again PV is equal to nRT. So P can be written as nRT by V here. So in place of P I am writing nRT by V. So here I am going to write, I am replacing this with nRT by V whole, this is V1 power gamma is equal nRT by V, this is V2 power gamma. So this T get cancelled. Now you can write this T1 V1, this is T2 V2. So this is T1 V1 power gamma, this is V1 power 1 will become 1 power minus 1 is equal T2 V2 power gamma minus 1. So this is the relation between volume and temperature of a gas in adiabatic process.